go. All right. We're kind of in the part of the course where we talk about the physical properties of the ocean, and we talked about ocean water and salinity. Right now, I want to move into geography a little bit and talk a bit about why the oceans are where they are and why ocean basins have the structure that they do. And to do that, we've got to touch briefly, just a little bit, on one of the most how do I put this, transformational ideas that anybody's ever had in the study of the Earth. That is the theory of plate tectonics. And in answer to a question that was posted on chat, yes, um, the printed slides for last week's lecture and today's will go up this morning. As soon as we're done here, I'll get them up as soon as I can. Right. So there's the Earth. Uh, the oceans are, of course, all interconnected, and they're sometimes called the world ocean. But we customarily divide these into 5 major oceans. I am hoping everybody knows where those are, but in case anybody doesn't, this is the Atlantic, between the North America, there's Canada, there's the US, South America's down here, and then over here, the continent of Africa and the continent of Europe. The Pacific is over here, and of course, it continues over there. The Indian Ocean right here next to the country of India. The Arctic Ocean is not fully seen in this projection, but the Arctic Ocean is what's at the North Pole. And the Southern Ocean is the ocean that surrounds the continent of Antarctica. It's this belt right here. Now, what defines these is, of course, the position of the continents. You know, the Atlantic is different from the Pacific because there's North and South America in the way, and there's not a very wide connection between them. They're also defined by the positions of distinctive current patterns, and that's going to be really important for looking at different environments in the ocean and, different life forms in the ocean. And I will cover that more in the next lecture. There's also a number of zones that are partially isolated from the larger oceans simply by the shape of the land. The most common name for these is marginal seas, but you'll see some of them. Hello, cat. Hey. Sorry, cat on the keyboard. Just a moment. What did you just do? You stupid cat. Right. Sorry about that. The most common name is marginal seas, but you'll sometimes see these called gulfs, bays, bights, um, various other terms. But we've already mentioned the Mediterranean Sea, which is right here, and the Baltic up here, and the Red Sea right there. We mentioned those talking about salinity. Those bodies of water tend to have salinity that's greater or lesser than the average in the ocean because of their partial isolation. And of course, you probably know the Gulf of Mexico up here, the Caribbean Sea south of it, south of Florida, the Gulf of California right in here between Mexico and the peninsula of Baja California, the Persian Gulf, noted because an awful lot of the world's oil flows through it, the Irish Sea between Great Britain and Northern Ireland, Hudson Bay in Canada for our Canadian students. I'm sure she knows where that is, and various others. If you look at the structure of the sea bottom, this is the globe as it might look if you sucked all of the water off of it. And if you color-coded it for various depths, you'll notice that surrounding North America and surrounding North Asia up here and surrounding all of the continents to some degree, when you if you were to start at the beach and start just walking out to sea, You first pass over a relatively flat, relatively shallow region called the continental shelf. The continental shelf is depths range from 0 to maybe a couple hundred meters, a few hundred feet. The continental shelf slopes down, but not very much. It's about a 1 degree slope. And you can see the continental shelf is pretty much the part that's shown in turquoise. All of this green and yellow and brown is land area today. The turquoise area is continental shelf. It's covered by water, but it's relatively shallow water. And the shelf may be wide or it may be very narrow. You can see it's pretty wide on the east coast of the United States and Canada. It's very narrow on the west coast, and there's various reasons for that. But narrow or wide, the continental shelf ends at the continental slope, where the land begins dropping down much further at a drop of about 2.5 degrees. That's enough that if you were, I think a 2.5 degree slope is about where they start putting warning signs for trucks to use their parking brakes and things like that. That's pretty noticeable. And the edge of the continental shelf, sometimes called the shelf break, is really the true edge of a continent. There have been times when sea level was lower, back in the Ice Age, back when the Earth was covered, well, not all of the Earth, but when large parts of the Earth were covered in glaciers. All of that frozen water had to come from somewhere, and it meant that there was much less liquid water in the hydrosphere. Sea levels dropped, and that's when there was dry land in between what's now the far east of Russia and Alaska, which may have been the route that the earliest Native Americans took, although I think they're finding it wasn't quite that simple. That's just continental shelf right now, but it was dry land because sea level was lower. There was dry land between Great Britain right here and the continent of Europe. In fact, there was a pretty rich, low-lying area of land right here called Doggerland. There would have been a connection between Newfoundland here and the rest of Canada, and so on. So the sea level might recede and expose some of that continental shelf, or it might rise and cover more of it. But regardless of sea level through time, the edge of the continental shelf is the real margin of the continents. And the continental slope gets cut by some submarine canyons. This happens to be a bit of the California coast. San Jose is right there where I've got the laser pointer. So now you know the way to San Jose. That was a popular song of a long time ago. The town of Monterey is right there. If you ever get to go to the Monterey Bay Aquarium. It's amazing. And there's a steep submarine canyon cutting across the continental slope. That's important because it's a channel by which shallow water sediment can get transported to the deep oceans. And that can be important for things like nutrient supply to the deep oceans. But the continental slope descends down to the abyssal plain of the deep ocean. And the deep ocean, this is given in meters. This would get down to 5,000, maybe as much as 6,000 meters. That's approximately 15,000 feet at the bottom of the Atlantic Ocean. The Pacific is even deeper than that. And most of the deep ocean is a pretty flat, level, frankly, kind of boring plain, very flat area. It may be broken by seamounts, mountains on the bottom of the ocean that don't break the surface. I might get to talk later as to how those form. And in the middle of the Atlantic Ocean, there is a buried mountain range with a cleft in the middle of it called the Mid-Atlantic Ridge. And in fact, if we go back, you can see it right there. And if we go back one more, you can see it right there. It's this curving line between North America and Europe and cutting around to between Africa and South America. And there's actually a whole series of mid-oceanic ridges. There's one right here, the Nazca Ridge, the 90-degree ridge right there in the middle of the Indian Ocean. And these are actually all connected, and they run all the way around the Earth, kind of like the seam on a baseball. So that abyssal plain is interrupted by mid-oceanic ridges. There are areas in which you would find oceanic trenches, although not in the Atlantic, and we'll talk about those in a bit. And every now and then you might get mid-oceanic islands if they break the sea surface, or seamounts if they don't. Which raises the question of why it all looks like that. And this is the guy who figured it out, Alfred Wegener. Guy with a mind that couldn't ever really be fit into one discipline. He got his doctoral degree studying the history of astronomy. He was a pioneer in the invention of weather balloons. I don't think he was the very first to invent them, but he was a leader in the idea of attaching instruments to high altitude balloons and sending them up to gather information on the upper atmosphere. And reading a book back in about 1905, he came up with the idea that the Earth's continents had not always been where they are located now, that in fact they had moved very slowly, really too slow to detect over the course of a human lifetime. But if you looked back in the past over millions of years, the Earth's continents would have slowly shifted. In fact, to be specific, about 250 million years ago, most of the Earth's land made up a single supercontinent called Pangaea, Pangaea, and Pangaea began breaking up roughly 210 million years ago, and the pieces of it had moved over the surface of the Earth, shifted to the positions that they have now, and in fact are continuing to move. Now, that was not widely accepted in his time, because on the face of it, it looks crazy. You know, North America is what, about almost 5,000 kilometers east to west and about 5,000 kilometers north to south, and it's mostly made of granite. You know, how is something that big capable of moving? Well, the short answer is that his idea was considered kind of fringe until the 1950s. In the 50s, Western countries started doing a lot of deep sea ocean exploration, using drill ships like this one, the Glomar Challenger, who were really getting down there and studying the rocks on the bottom of the ocean, using newly developed techniques like sonar to map the features of the bottom of the ocean. These days, we can learn a lot from satellites as well. And really seeing what was down there. I should mention that this all had to do with the Cold War. The reason we got very interested in the depths of the ocean is because, you know, if you have a good map of the depths of the ocean, you've got good places to hide, things like your super secret listening devices and your nuclear missile armed submarines. The Glomar Challenger gathered an enormous amount of really important scientific data, but its real purpose was to fish up wrecked Soviet submarines and steal their code books, which in fact they did. They did manage to recover a Soviet sub, and steal its codes and its technical secrets. So this is all happening in the context of the Cold War. But all of that new data flooding in, gathered by ships like Glomar Challenger when it wasn't stealing subs, led to the formation of a modern body of theory called plate tectonics, and it was mostly complete by about 1965. And this is the framework for understanding most of Earth's geology, including the shape of the oceans, the topography of the oceans. And it goes like this. If you were to slice through a continent, there's, trees and flowers and various types of rocks on the continent, but most of it is granite-like rock. And the average density is about 2.6, 2.7 grams per cubic centimeter. Rocks on the bottom of the ocean are just a bit denser. They're a bit more rich in iron, and they're about 2.8 grams per centimeter. And both the continental crust that makes up the continents and the oceanic crust that makes up the floor of the ocean are literally floating on top of a body of even denser, hotter rock underneath. That hotter rock deep underneath is called the asthenosphere, aka the upper mantle. Underneath the crust, there's a very thick layer of very hot rock called the mantle, and under the mantle, we get to the Earth's core, which is divided into inner and outer. That'd be a whole nother lecture to talk about how we know that. But the asthenosphere, the density is about 3.3 grams per centimeter, so it's heavier. And the asthenosphere is extremely hot, but it's also under extremely high pressure. So it's not really a liquid. Sometimes people think of the plates of the Earth as floating on top of an ocean of liquid rock, but it isn't really. The mantle is solid, but it's under such high pressure and at such a high temperature that it behaves, it's a very viscous solid. It's not like molten, it's not like a liquid, but it's closer to something like peanut butter, which is solid, but nonetheless is capable of some degree of flow. I guess floating on an ocean of peanut butter is probably the best metaphor I can come up with, at least at this time of the morning. And both continental and oceanic crust form tectonic plates, and they float on the asthenosphere. And by the way, this means that the legend of the lost continent of Atlantis can't be true, at least in the form it's often told. You couldn't have an entire continent sitting in the ocean and then suddenly sinking into the sea for the same reason you can't have an ice cube in a glass of water and have the ice cube suddenly drop to the bottom. The rock that makes up the continents is too light to sink to the bottom of the ocean spontaneously. Now, the legend of Atlantis is thought to have been based on some islands in the Mediterranean that were destroyed by volcanic eruptions, and that's another story. I can't go there. But this is a map of the tectonic plates. The North American plate includes the continent of North America, plus a decent chunk of Russia, plus Greenland and all of the seafloor surrounding them. It consists of both continental crust and oceanic crust. The Pacific plate over here in yellow is almost entirely oceanic crust. There's the South American plate, the African plate, the Australian plate, the Indian plate, and there's a number of smaller plates. The Juan de Fuca plate off the coast of the Pacific Northwest, the Scotia plate here in the South Atlantic. Saudi Arabia basically makes up its own plate. The Filipino plate right there. Unfortunately, China is now part of the Eurasian plate, so we don't have a China plate. That was a joke. China plate. Never mind. Right, right, right. Hardy har har. Okay. You'll notice the little arrows on them, and the plates are not standing still. The plates are moving with respect to another, which means that some of them are running into each other and some of them are pulling apart. And plate margins are often associated with earthquakes and volcanoes, and there's various reasons for that. These red dots on this map are earthquakes of greater than magnitude 5 between 1980 and 1990. This is essentially earthquakes that are big enough to feel and big enough to rattle your house and knock things off the shelves. And the yellow lines are plate boundaries. And you can see that the vast majority of earthquake activity happens along plate boundaries. This is particularly prominent in the East Pacific right here, which has a ridiculous number of earthquakes. There are also a sizable number of volcanoes in the East Pacific, and there's reasons for that, for why they're there. And this prevalence of earthquakes and volcanoes is why the margin of the Pacific Ocean is sometimes called the Ring of Fire. So right there's the burning ring of fire, as Johnny Cash would have said. So there's a great deal of geological activity along the edges of plate margins. There's a few places where you find them in the center of plates, like Hawaii right there, East Africa right there, and there's various reasons for that. But you can see that there's a very strong correlation between quake activity and plate margins. If you match up the outlines not of the coastline, because the coastline shifts with sea level, but the continental shelves, the fit between the Americas and Eurasia and Africa is nearly perfect. It's actually been looked at via computer analysis, and it's been shown that there is essentially almost no chance that a fit this good could have appeared simply by chance. This is not just random chunks of land that happen to fit together. This points to a single supercontinent called Pangaea that began breaking up approximately 210 million years ago. Right. Okay, there is a stonking huge amount of evidence that Wegener was fundamentally right, and a lot of it we just don't have time to get into in this particular course. Wegener looked at everything from the distribution of different groups of animals and plants that are now on separate continents, but you could explain it by assuming the continents had once been close together, had been joined. We now have evidence from, if you push the continents together, geological features line up. Like, for example, the Appalachian Mountains go up the east coast of North America, and if you push them together, you can see that they actually continue into the highlands of Scotland and the Kjolin Mountains of Scandinavia. Those are all part of a single mountain chain, and there's various other features that match up. The simplest way now is that we can now measure it directly with GPS technology. It's been possible for years to use much more sophisticated GPS receivers than the ones in your cell phone and measure the rate at which continents are moving apart. And it turns out to be between 2 and 20 centimeters per year, depending on where you are. This is roughly somewhere between the speed that your fingernails grow and the speed that your hair grows. That's about how fast they're moving. Although they're not moving smoothly and evenly, sometimes they might not move for a long time and then suddenly jump apart. And in that case, you get earthquakes and things like that. Wherever you've got two plates that are moving apart, we call that a divergent plate boundary. And what you'll see on the ocean floor at a divergent boundary is a mid-oceanic ridge. Where you have two pieces of continental plate coming together, when two pieces of continental crust hit, you get a fold belt. You get an area where both of the continents crumple like the fenders of two cars crashing into each other, and you get a particular type of mountain range. We're actually living in one. The Ouachita Mountains of Arkansas are an ancient fold belt. And this is why if you, one moment, Aaron, not the Ozarks. And this is just for me, please. I know you're interested, but please don't jump in. It kind of throws me off. Apologies. Thank you, kid. Sorry, my son was giving some helpful commentary in the background. Right. Anyway, that's why when you look at the rocks around Conway, if you drive through a road cut, they're all crumpled. They're no longer horizontal layers. They've been bent like a beer can against my grandmother's forehead. More recently, the Himalayas, the European Alps, those are fold belts that are, in fact, still rising today because you have plates that are coming together, crashing into each other. When you have an area of continental crust and oceanic crust coming together, we call this another type of convergent boundary, and it forms a structure called a subduction zone. And then finally, your third option is when two plates move past each other, and we call that a transform plate boundary or transform fault. Mid-oceanic ridges are places where continents are moving apart, and along a mid-oceanic ridge, new continental crust is constantly being made. One of the big findings of plate tectonics is that oceanic crust is constantly being destroyed and constantly being created. It has not always been there since the origin of the Earth. It's actually over the really long time span, it's constantly being recycled. And new oceanic crust is being produced at mid-oceanic ridges. And here, as two plates pull apart, rock wells up and fills the gap between the two plates, solidifies, and it forms new crust. You'll also see this called seafloor spreading. So new crust is constantly formed right at the center of the ridges, and then it gets pushed to the side, and another round of new crust forms, and older crust is constantly being pushed away. So these are the main mid-oceanic ridges where seafloor spreading is taking place. I pointed out the mid-Atlantic ridge running right down the middle of the Atlantic. The East Pacific Rise is a big one. The Central Indian Ridge, also called the 90-degree ridge, is right there. These are the places where new crust is being built. And if you could see it in cross-section, it would look like this. I said that the asthenosphere is solid, but if you get to an area where the plates are very thin, without that pressure, the melting point goes down, and there's a zone of liquid rock right here. And that zone of liquid rock in the asthenosphere pushes its way out between the plates right there and solidifies to form new crust. And then older crust gets pushed to the left and to the right. Older crust is constantly getting pushed this way and that way by the force of magma, liquid rock, pushing its way between the plates and forming new crust. And then the new crust gets pushed to the side and new crust gets formed in the gap and so on. So this is where oceanic crust is being born. We can use various techniques that I don't really have time for to get to date the age of rocks. That's a whole nother set of lectures, and I probably won't have time, but you can look up radiometric dating. That's why the gods gave you Wikipedia. And the crust nearest to the mid-oceanic ridges is the youngest, and that's the rock shown in red. That's the rock that's forming even now. Oh, by the way, right there is one of the few places where a mid-oceanic ridge comes out onto land. That is the island of Iceland. And in fact, there is a deep valley called Thingvellir in Iceland where you can quite literally walk over a little bridge between North America and Europe right there. And Iceland, of course, has a great deal of volcanic activity. In fact, recently, I think they had a town destroyed by a recent volcano. So that's one of the few places where we can see this without going down to the bottom of the ocean in a submersible. So the youngest crust along this red line is forming now, and the age of the crust gets older and older on either side, and the oldest crust is shown here in dark blue along the coast of North America and the coast of West Africa. And that rock is only about, I think, 180 million years. And in fact, there's no oceanic crust anywhere on Earth that's older than about 210 million years. Whereas, for example, all of the rocks making up the Ozarks and the Ouachita Mountains are older than 210 million years. Some of the Ozarks are twice as old. Parts of the Ozarks are maybe about 8 times as old as that. So the continental crust does not get created and destroyed in the way that oceanic crust does. Oceanic crust is constantly being born. It's created at these ridges. It gets destroyed at convergent boundaries. And so, yeah, oceanic crust relatively young compared to some of the very old rocks that form on continents. Another little Cold War bit. In the 1950s, as people started putting nuclear missiles on submarines, people realized that in the event of a global thermonuclear war, submarines were the only missiles that couldn't be detected and hit. So both the US and the USSR started trying to develop detection systems. And one of these was very sensitive magnetic field detectors called magnetometers. And they started towing these over the ocean floor. It turns out that in some areas of the crust, the magnetic field of the rocks on the ocean floor was pointing in the same direction as the Earth's own magnetic field. In other areas, the rock's magnetic field was pointing in the opposite direction as the Earth's magnetic field, canceling it out. And what's weirder, those zones form stripes running parallel to mid-oceanic rifts. And the stripes were symmetrical with respect to the rifts. You got the same patterns on either side. And you get something like that. At the crest of a mid-oceanic ridge, the rocks that are forming right now, as they cool, they take up the magnetic field of the Earth. You could think of them as being like a lot of little compasses whose needles are permanently frozen in the direction of magnetic north. However, remember that you get older and older rocks as you go to either side of a mid-oceanic ridge. So you get older rocks here and here. And I can't really write very well on this thing that says older. I hope you can recognize that. And we now know that the Earth's magnetic field periodically flips. exactly why has to do with the physics of circulation patterns in the Earth's deep core. That gets into much heavier physics than I can really get into. But every so often, if you were standing around, you would notice that your magnetic compass needle would stop pointing to the north, and over a few hundred years, the magnetic field would fade out, and then it would come back in at the opposite polarity, which means your compass needle would start pointing to the south. And rocks that are formed during eras of reverse polarity retain that reversed magnetic field. So these light stripes right there are rocks that formed at a time when the Earth's magnetic field was reversed. And those rocks retain that reversed magnetic polarity. And you can see how they form stripes on opposite sides of a mid-oceanic ridge. And the pattern of the stripes are mirror images of each other. They're symmetrical on either side of the ridge. So there, we know that the Earth's magnetic field periodically flip-flops, and igneous rocks that form at a mid-oceanic rift are magnetized by the Earth's magnetic field once they cool down below about 600 degrees Celsius. That's called the Curie temperature. And they retain that field even if the Earth's own magnetic field flip-flops later on. And so the result is we get these symmetrical stripes of rock with alternating polarity on either side of a mid-oceanic ridge. So that was a critical discovery in working out how this model of ocean crust formation actually works. There's some actual stripes measured off the coast of Iceland along the mid-Atlantic ridge, color-coded for clarity. And you can see we've got this symmetry across this more or less straight segment of the ridge. And we get similar patterns that you could find if you looked elsewhere in the world. Okay, right. So that's what's going on at mid-oceanic ridges. And as we'll see, with volcanic activity, with molten rock coming up along mid-oceanic ridges, that creates some extremely interesting ecosystems for living things in the oceans. We'll talk about deep sea hydrothermal vents coming up in, might not be till towards the end, but we will get to this. This does some really cool things to ocean life. So if new crust is being formed, either the Earth is blowing up like a balloon, which it is not, or there has to be a way for crust to be destroyed. And oceanic crust is being destroyed at areas called subduction zones. And that's where one piece of oceanic crust sinks under another plate, gets pushed down into the asthenosphere, and ultimately, over many millions of years, mingles with the rest of the asthenosphere. You can always tell a subduction zone because it's marked by a deep sea trench. Mid-oceanic ridge is like an underwater mountain range, but at subduction zones, you get trenches. And running parallel to the trenches, you get zones of volcanoes that are called island arcs. And examples of island arcs would be things like the Aleutian Islands, the Philippine Islands, Japan, most of Indonesia. Hawaii is not an island arc because it's not formed by subduction. But here's a diagram of a cross-section of what this would look like. You have an oceanic plate, and the plate is moving, there, I'm on pen, is moving this way, where it starts sinking under the other one. You get a trench. Back of the trench, you get a lot of the sediments that used to lie on this oceanic plate get scraped off and stuck to the plate that's riding on top. That's the subduction complex. When I was in grad school in Berkeley, California, one of my fellow grad students was studying fossils from these ancient sediments that used to sit on top of an oceanic plate and then got scraped onto North America when that ancient plate sank down. Most of the bedrock of the city of San Francisco, for example, is a rock type called the Franciscan complex, and it's all ancient sediment that got scraped off a plate called the Farallon plate and stuck onto the edge of North America as the Farallon plate itself sunk under North America. So you get sediments and things get scraped off in the subduction complex, and then the plate starts sinking down and drops into the asthenosphere. Right about here, I said the asthenosphere was mostly solid, but rocks on top of the plate are saturated with water, and that lowers the melting point of the rock, which means that rocks on the top of the oceanic plate that's sinking down start melting. You get this big blob of liquid rock, and that rock rises to the surface, and you get a chain of volcanoes that's always parallel to the subduction trench. And that's what an island arc looks like. And they're called arcs because on a flat map, they usually have a gentle curve. If you want to know why it's an arc, take a knife and cut into an orange at a shallow angle, and you'll see that your cut makes an arc. It's the same thing here. They're arc-shaped as a consequence of the fact that the Earth is round. And it really is. It's round, I'm telling you.
No way, really?
Just so everybody knows. Now, we can actually see this because seismic waves, the shock waves made by earthquakes, by nuclear tests, and other really big high-energy events, the shock waves travel faster in cold rock than they do in hot rock. And if you have a network of seismographs, seismic wave detectors, and very accurate clocks, you can measure travel times between the place where seismic waves are generated, between the focus of an earthquake or something like that. You can measure the travel times of those waves between where they're generated and where you are. And that travel time depends on rock temperature. So with all that travel time data, you can put it together and make a model of zones of colder and hotter rock. And this is really cool because this lets you take almost like an ultrasound picture of the asthenosphere of the Earth. So this is a cross-section of the Tonga subduction zone in the southern Pacific Ocean. And this blue area right there is the edge of the Pacific plate, and part of it is sinking down into the asthenosphere. And you can see it maintains its identity all the way down to about 600 kilometers. One moment. Aaron, be quiet while I'm lecturing. If you can't, go to your room, please. Right. So that's the plate subducting down, and you can see it as this slab of relatively cold rock all the way down to about 600 K. Right here, you've got this pool of liquid rock. That's the part of the plate that's melting because it's got a lowered melting point, and that liquid rock is rising up and forming, there's an island arc right there, the Tonga arc and Fiji right there. All of those are being fed by that pool of liquid melted plate rock. So this is really cool to see because it very much shows, what our model is supposed to look like. A really beautiful one is the Aleutian Islands. This is Alaska. Let me go back to laser pointer. Right up here. This is the Russian Far East. This bit down here is called the Kamchatka Peninsula. And this chain of islands right there is the Aleutians. Continuing on to part of the Aleutian chain is stuck to the Alaskan mainland. This is, I think, the the Katmai Peninsula right there. So sometimes the islands may be incorporated into a part of a continent, as has happened here. And the Pacific plate is moving that way, more or less northwest. And right along here, it's sinking under the Eurasian plate, and we have this trench called, sensibly enough, the Aleutian Trench. There, I'll make it blink on and off. Ooh, computer animation, how sophisticated. So the trench is right where the Pacific plate is diving under the Eurasian plate. Just back of the trench, just behind it, we have this chain of volcanoes driven by the melting of water-saturated rocks on the plate as it sinks down, and they're all potentially active. There are periodic eruptions in the Aleutian Islands to this day. There's not an awful lot of people living on them, but there are some, and every so often they have to be evacuated. So that is a beautiful example of an island arc connected with the sinking of a plate. The deepest part of the ocean is the Marianas Trench, and this is a place where the Pacific plate to the right is sinking under the Philippine plate. So the Pacific plate is moving that way relative to the Philippine plate. And the Marianas Trench marks the subduction zone. That's the very deepest part of the ocean. The deepest part of the Marianas Trench, known as Challenger Deep right there, is 11,000 meters deep. That's 36,000 feet. That, by the way, is deeper than the highest mountain. You could theoretically sink Mount Everest in Challenger Deep, and it wouldn't break the surface. It wouldn't come anywhere close to breaking the surface. Is there life down there? This being a marine biology course, you might be wondering when I'm going to get to the biology. In fact, there is. The first submersible to get down to the bottom of Challenger Deep was a purpose-built research vessel that was operated by the Navy called the Trieste, which did get all the way down very briefly. More recently, there have been some other expeditions, and the most famous one was the Deep Sea Challenger, built by James Cameron, who made a ridiculous pile of money off the movie Titanic and has decided to put it towards things like ocean exploration. I mean, I'm sure the guy owns a lot of houses and things like that, but he's actually using his pile of billions for research as well. And so he's actually gone down there, and there are life forms down there. They're pretty hard to study, as you might imagine, but we'll talk more about that later. But there is life all the way down to the very, very deepest part of the oceans. So, good to know that, even if we destroy life up here on the surface, I believe that our life will go on. And one of the cats just hissed at me. Sorry about that. Right, right, right. Okay. Hey, I can hit those high notes. Give me credit. Okay. All right. Shoot. And I have just realized it's 9:50 and I don't have time to talk about transform boundaries, which happen when plates move side to side with respect to each other. And they look like this. Those green lines right there are transform boundaries. And one that crosses onto land is the famous San Andreas Fault. And I'm going to have to stop there because we are out of time. So maybe I'll pick up a little bit of that on Friday, but I'm going to go ahead and stop the recording now.